Yeah. You know, this is actually not the worst looking circle I've ever produced, so it's not that bad. I'll take it. I just figured if you don't have a compass to draw a circle, then why am I using one? You know. So I'll do it freehand. When we do the quiz, I'll give you on the handout. I'll show you exactly what it looks like in a little while, but on the handout it'll have circles and lines and everything already drawn for you. But for now, I just wanted to kind of take it from scratch. All right, so we have a center of a circle. We extend out to a point along the x-axis. In theory, that's along the x-axis. And, that's funny. It just looks like from the movie Oblivion, one of those remotes. Anyway, so what we want to do is really just kind of focus on first what the unit circle is and then the structure of it. Right? The unit circle is called that because it is a circle with a radius of 1, a single unit in every direction. That's why they call it the unit circle. But what that means is that we're looking at a point. If I'm on the x-axis, that point to the right would be 1, 0. Right? We also define this location as being at the 0 degree mark. All right, 0 degrees is for some reason to the right, even though in real life it's not. All right, we consider 0 degrees to be due north, which is not what that looks like, but that's just how we do it. All right, so we kind of get a sense of orientation from this, and go from there. So also in radian form, it would be 0. All right, so 0 degrees and 0 radians. I'm going to try to keep my color scheme pretty consistent. All right. What we do is we work around in the unit circle. I mean, we could do your coordinate axes, so go 90 degrees and so on, and build it out from there. But I want to actually start with a 30-degree rotation and then work off of that. All right, just so I can draw some triangles, show you where some things are coming from, and so on. So if I were to shift up, rotate up, 30 degrees. I'll make a note of it right here. I'm going to drop an altitude. If I know the radius of the circle is 1, that means any hypotenuse I draw, which would go from the center of the circle to a point on the circumference, would have a length of 1. Okay? So then what I would do is try to figure out what the opposite and adjacent sides are. So I know that this is a 30-degree angle. I have a 90-degree angle, so the missing one would have to be 60 degrees. So I have a 30, 60, 90 right triangle. There's a couple of ways that you could figure out what the measures are of the lengths of the sides. One way would actually be to use your calculator, but we know that sometimes with trig, the calculator gives us some funky values that we don't really like. Right? Another way to do it would be to know your 30, 60, 90 relationships. Right? But what it really boils down to is the idea, without deriving everything, is that anytime you're in the unit circle and opposite a 30-degree angle, you're looking at a length of 1/2. And opposite a 60-degree angle would be a length of radical 3/2. Right? And you can justify that by using the Pythagorean theorem. Right? So that tells me that I have a coordinate here, because a coordinate is a horizontal movement followed by a vertical movement. A coordinate of radical 3/2, comma, 1/2. All right, so we have our first coordinate for our unit circle. Now, in terms of radians, if you know the conversion factor, then that's pretty easy. Because, and I'll just make a note of it off on the side. Pi radians is equal to 180 degrees. All right, that that's the conversion factor we use, but it really comes from the idea that one full turn around the circle is equal to 360 degrees. It also happens to be equal to approximately 6.28 or 2 pi, right? And what a radian is, just to refresh, and actually to teach, because some of you may have never even learned this. A radian is an arc length around a circle that has the same length as one radius of that same circle. So basically, if I took a piece of string, for example, and stretched it out to the length connecting the center of the circle and the circumference, so one length of the radius, and then just wrapped it around the edge of the circle, I have an arc length. If I saw how many times those arc lengths went into the total of the circumference, then I would know what 360 degrees is equivalent to in radians. It turns out that you get a little bit more than 6 1/4 of those full radius values in one full turn around a circle. Turns out it ends up being 6.28 approximately, which is 2 pi. So if 2 pi radians is equal to 360 degrees, then pi radians is equal to 180. So how's that useful? Well, I could just do a quick quotient here. We're looking for 30 degrees. So I can make 180 into 30 by dividing by 6. Looks like a G. All right, so 180 over 6 is the same as 30 degrees, but that's telling me that 30 degrees is the same as pi over 6 radians. All right, so we have that conversion. We can use the pi over 6 being equal to 30 degrees to help us find some other things down the line. But let's move on to the next special angle, which is 45 degrees. So I'll make a note of that over here somewhere, 45 degrees. Kind of chuck it in here, 45 degrees. I'm going to drop an altitude again. Also 45 degrees up here. Okay. In the unit circle, and the unit circle is defined again by the fact that the radius is always equal to 1, meaning the hypotenuse will always be equal to 1. Anytime you're opposite a 45-degree angle using your 45, 45, 90 right triangle rules, we would be looking at measures of radical 2 over 2. So that's telling me that the coordinates, because again, coordinates are x comma y, would be radical 2 over 2 comma radical 2 over 2. All right, in terms of the radian measures, I just think to myself, how do I get from 180 to 45? Well, if I chop 180 in half, I get 90. If I chop it in half again, half of 90 is 45. So that's telling me to divide by 4. All right, so that's telling me that pi over 4 would represent the radian measure for 45 degrees. All right. That's the hardest part of construction of the unit circle. And just bear in mind, when you're doing this on a quiz, you're not going to have to draw out all these triangles. That's all instruction. That's all me trying to explain to you the why rather than just the how. I just noticed that some of my stuff went off the screen, so let me just do this really quickly.
The unit circle test, we're just going to have to create this and that's it?
Yeah. And then that's all there is to it. And again, I've said this a few times. I don't know where your story ends in terms of math. If it ends here, then this is it's all academic. It's all for you to just learn for the sake of learning. But if you're sitting in my Calc 3 class in the spring, you're going to be like, one of two things. It's going to be like, oh, thank God I really practiced that unit circle. Or, oh, damn it, I should have practiced that unit circle. It's really one of those two things. We are going to, there's something called, we're going to work with spherical and cylindrical coordinates. All right, spherical and cylindrical coordinates are I'll just talk about cylindrical for a second. It's a coordinate system in 3 dimensions whose base is the unit circle. You don't get coordinates without knowing the unit circle. Right? So if I have some point floating around in space, I can define that based on some rotation and then a particular height. But that rotation is defined specifically by the unit circle. I mean, there is no chance of understanding it whatsoever unless you have a handle on this. All right, so I'm going to hit you hard with it now, and then if you're in my class, you'll thank me for it. If you're not, well, I don't know.
Is there some concept we're supposed to understand, or are we just memorizing?
No, the concept is how to build it. Yeah. And so the relationships that exist within this entire unit circle are really structured based off of the first 2 triangles. Because once you have the first 2 triangles, everything else works itself out. Right? So if I create my 3rd triangle, which would be at the 60-degree mark, all right, so 60 degrees would make this vertex angle 30 degrees. And so what's happening? I'm looking at a triangle. It's got a hypotenuse of 1. The 2 angles are the same as my first triangle, just in a reverse order. All right. So what that would mean is that this length would have to be the 1/2, and the vertical length would have to be the radical 3/2. So I'm just doing a switcheroo on my coordinates, 1/2 radical 3/2. All right. So, and again, that's because in the first triangle, opposite the 30 was the 1/2, but that was a vertical line segment. In this one, opposite the 30 is a horizontal line, but it should also be valued at 1/2. All right. I don't want to write it in because it's already getting too messy. You know, on the triangle, it's already getting too messy, but that's enough to know. Now, cofunction relationships are very useful, and this is the trig, conceptual part of it. So you'll notice how the x value at 30 degrees is the same as the y value at 60 degrees. And so that kind of feeds into the idea of, okay, so why are we learning about this? We're just putting numbers on a triangle. The x value in any coordinate on the unit circle is the result of cosine of some angle. The y value is the result of sine of some angle. So from the unit circle, I can get all 6 trig functions at these special angles. And there are some other special angles, but they don't really lend themselves to this because, like, I don't want to label, I think it's 15 degrees with the x value of, I want to say it's radical 6 minus radical, no, it's radical 2 minus radical 3/6, I think. I don't know. But anyway, the moral of the story is it's not pretty. So these are the more concise angles, or at least the ratios related to the concise angles. So anyway, I now know that at 30 degrees, I have a cosine equal to radical 3/2, a sine equal to 1/2. That corresponds to 60 degrees, right? So 60 degrees has sine of radical 3/2 and cosine of 1/2. So why is that important? Well, cofunctions, if you have cofunctions of complementary angles, they're always congruent. Equivalent. Congruencies. Right? So if I know, for example, the cosine of 10 degrees, if I know that number, then I also know what the sine of 80 degrees is. Right? Because complementary angles work that way in cofunctions. All right, so it's not just limited to this. Like you can hopefully see the application of it, especially with some of the things that we're doing with integration, where you have maybe in one particular form, the calculation is not something you can come up with, but just by tweaking it a little bit, you're able to come up with something more reasonable. You know, it's just another tool for you. All right. Then we go to 90 degrees. So to kind of take a break from the madness. We're going straight up, 1 unit, which means that our coordinates are 0, 1. We're at 90 degrees. I realize at this moment that I did not state the radian measure for 60 degrees. Okay, so I go back to my relationship here and I say, I don't know why I erased the fraction bar. Yeah, pi over 3, because I'm taking the 180, I'm trying to make it into a 60. To do that, I divide by 3. And so that's where my pi over 3 comes from. Okay. I do the same thing for the 90. A little easier to see, probably. I want to make my 180 into a 90, divide by 2. So pi over 2. There's like little mnemonics that'll help you figure out the radian measures. But I encourage you to at least get a feel for why it works the way it does before you settle for just rote memorization. Because aside from the unit circle quizzes, like every unit test, you could create a little note card. I mean, I have had situations where people would put the entire unit circle on their note card. I think that means that you don't understand how the unit circle works, because, well, for 2 reasons. One, because if you had to put it on there to begin with, you're probably not up to snuff. But also, once I get around to it and show you the rest of the whole thing, you'll realize, or at least if you have a good understanding of this, that you don't need the entire unit circle in order to get the information that you need. You just need the first quadrant. All right? And this is going to work really well when we start talking about inverse functions. Tangent is not, but since tangent is sine over cosine, we just do the divisions. The second unit circle quiz is going to ask you to also state the tangents. The first one won't. But when it does ask you to state the tangents, you're just taking this and putting it over that. So 1/2 over rad 3 over 2 just simplifies down to 1 over rad 3. Negatory on the calculators. No calculators. No calculators, no notes. It's just you versus the assessment. And you'll come out victorious. Except for one of you. There's always one. And I take no joy in that. But there's always one person who's either like, oh, you were serious. We really are taking a quiz on this. Okay, I don't know how to do it. Or the, that's tonight moment. I thought it was next week. I'm completely unprepared. So, yeah. I always hope that just bringing it up is enough to stave that off, but it never is. Oh, my drawing ability is. Ugh. Yeah, but just don't resort to cheating. Just please don't do that. I had a student who did that last semester, and it was just like on a unit circle quiz. So basically, college algebra and trig content. You're in Calc 2. Well, he was in Calc 3, and he cheated on that. It's like, wait, so you had to cheat on something that was 4 classes before the one that you're in, 5 classes before the one that you're in? That's terrible. So, yeah, and also, just so you know, I'll give you the reveal now so that you don't go into panic mode. Hopefully it won't be that kind of situation, but the second unit circle quiz, because it involves tangents, is obviously a little bit more challenging, but I always take the second score if it's higher than the first one and replace the first one with the second score. So basically, you'll get another crack at let's say you bomb the unit circle quiz on Monday. When we take the second one, if you do well on that, I'll replace the bomb with the score you get on the second one because it means that you will have done better on something more challenging. So why not give you that opportunity? All right, so that's not quite as good as meeting with success both times, but you know, actually, I guess it could be if you get 10 out of 10 the second time. But yeah, it's not the end of the world the first time around. It's kind of like a dry run. So that's even more motivation not to cheat. So actually, so when somebody tries to cheat, they'll be incredibly humiliated when they find out that the score could have gone away anyway. It's just the way things are. Don't cheat. You guys are so great. Don't cheat. Please don't. No, nobody in here is going to cheat. I don't even know why I'm bringing it up. It's just somebody always does. Somebody always tries to, and I don't want you to.
So is it vice versa, or is it just like if you do really bad?
If you bomb the second one, you're stuck with it. Yeah. Although I am toying with possibly having a third one, time permitting. So, but whatever the last one is, you're stuck with that grade. So. Still haven't kind of figured that out. More reciprocal functions, like maybe throwing a cosecant in there or something. I don't know. I haven't really thought that one through. But anyway, so but like I won't just spring a third one on you without letting you know anything. Everything else is some sort of reflection. Actually, they're all rotations, but a reflection of what's going on in the first quadrant. So I already have the coordinates because anytime I reflect over the y-axis, I'm negating the x value. Right? Same y value, different x. So that's telling me that I'm looking at negative 1/2, comma, root 3 over 2. Negative root 2 over 2, positive root 2 over 2. Negative root 3 over 2, positive 1/2. Right? And that's all again because we're reflecting over the y-axis. So then that tells me that I can get all the coordinates on the bottom because every one of those is a reflection over the x-axis. When you reflect over the x-axis, you're negating the y value. Although my diagrams don't look like reflections, we just have to kind of suspend our disbelief. Oh, I missed the negative 1, 0 here. It's actually the most common error on unit circle quizzes. I've been giving them for years, multiple times per year. Forgetting the quadrantal angles, the ones on the axes. And also, sometimes this is a little less frequent, but sometimes people transpose them and write 0, 1, 1, 0. That to me is a little bit more egregious because what it means is that you're just trying to, you're taking a mental snapshot of the unit circle, maybe possibly like 2 minutes before the quiz. You're like, okay, what does it say? What does it say? Okay, try to remember, and then, and you have no idea why it works the way it does. We've all been there though. Just think about it. If these were actually coordinates on a graph, this would be on the x-axis. So it has to be something comma 0. So why you put 0, comma 1 is just beyond me.
You want us to actually draw the triangles?
No. You just give me the bare bones. So I'm going to negate all the values of y in each of the coordinates that I have in my northern hemisphere. So keep the x values the way they are, negate the y values. And I haven't forgotten about all the other stuff, like degrees and radians. So we'll address that in a minute.
ask a real-world application of the unit circle?
Oh, that's actually pretty easy. Navigation, any kind of navigation, because the entire planet is circular in nature, because it's not flat apparently. I have no idea. It's crazy.
And according to some people.
According to some people, yeah. So yeah, it's just spherical coordinates are related to just global positioning. Global positioning is like the essence of movement on Earth, and so that's all based on unit circles. Not specifically these angles, but this is the essence of that.
You don't do all the transpose the rest of the unit circles for that transition. That's so beautiful.
No, it'd be right, but that would not put me in a good mood. I'd be like, dang it, now I gotta figure all this out. It should be all right once I realize what you did, but it's gonna be one of those moments. I actually had a student who, and it's pretty clear when I give an assessment, it says name, date, possibly the class that you're in. So I don't know how he missed this, but he filled out the entire unit circle upside down and turned it in. So I graded it. Everything was wrong. He did very poorly. And so I came back to him. He looked at it. He said, "Oh no, I wrote it all upside down." So I turned it upside down, wrote his name upside down, and regraded it, and it was fine. But yeah, stuff like that happens. It's not the end of the world. But yeah, you just definitely want to be on the lookout for things like, I don't know, the orientation of your paper while you're working on it. I wanted to go the other way. Zoom. Let's go 100. Yeah, there we go. All right, so we got the north, we got the south. I guess we're in good shape here. Now in terms of the angles. So in the first quadrant, these relationships are consistent. In the first quadrant, we have 30, 45, 60 degree reference angles. So really more basic than that. I'm increasing by 30, 15, 15, 30. So do that all around. So from the 90, I want to go another 30, 15, 15, 30, another 30, 15, 15, 30, another 30, 15, 15, and 30. So then the only challenge that remains is the radians, right? And so we can work off of what we have in the first quadrant to help us figure that out, right? So it's just basically, and it's all without a calculator. I haven't even looked at a calculator yet. If I want to get to 120 degrees, I could work off of what I have here. 60 degrees is half of 120, right? So if I want to get from 60 to 120, I would just double it. So 2 pi over 3 would be double the pi over 3. When I want to get from 45 to 135, well, I wouldn't double the 45, that just gets me to 90. Add another 45, meaning triple the 45. You get to the next one. I can look at the 30 degree angle and say, well, how do I get from 30 to 150 multiplied by 5? All right, 180 is pi, otherwise we can't do any of the stuff that we've been doing. And then you just keep working around that way. 210 is 7 times 30, so 7 pi over 6. 225, you could actually look at it in terms of movements, and that's something I encourage you to do. Just think about the physical movement that gets you from one location to another. That's going to help, because the hardest thing about Calc 3 is the spatial aspects of it. Right? So this is a 45 degree movement. I need to get here, so I'd have to go 1, and it's a half of this quadrant turn basically. So 1, 2, 3, 4, 5. 5 of those movements to get to that location at 225, which, and since it's, each one of those movements is pi over 4, I'm looking at 5 pi over 4. 240 is double 120. 120 is 2 pi over 3, so double that, 4 pi over 3. All right, if I wanted to get to 270, maybe I take my 90-degree angle and work off of that. 3 of those 90-degree movements would get me there. So 3 pi over 2. 300 degrees, a bunch of different ways we can get there now. I might do double the 150. I might do 10 times the 30. We can do 5 times the 60. I like 5 times the 60 because that puts it in reduced form. The other ones give me 10 pi over 6. I got to do an extra move to get there. But either way, it's fine. To get to 315, I have to do 2 more of those pi over 4 movements. So 2 more of them will put me at 7 pi over 4. 330, well, that would be 11 of those 30-degree turns. So 11 of those pi over 60s. And by definition, 360 is equal to 2 pi. All right. So that's really the unit circle, and this is the starting off point to understanding rotational trigonometry. But there's a lot to it. Now, there's like little mnemonic devices that you may have learned about over the years. I know there's like a way of doing it with your hand, but I think it involves writing on your hand. I don't know. I knew it at one point, then I lost track of it, then I knew it again, then I lost track of it again. But one of the relationships that is probably most helpful, because in my experience, I don't know if this is you necessarily, but in my experience, people generally don't have a problem with the degrees. They usually do pretty well with the coordinates. Sometimes folks will transpose these two guys, but that happens. That's just a whiff. It happens from time to time. If people get jammed up on this, it's the radians. I mean, I've had people stare at this for a long time, taking the quiz, and I'm like, wow, they're still going there. And you're just kind of staring at it. Turned out they were staring at the quiz for like 30 minutes looking for inspiration on how to come up with the radians. And you just don't have it. So they end up turning it in and be like, all right, well, there goes that grade. So how can we get the radians without inventing them every single time? Well, you look at patterns, that's how. Just like everything else in math. It looks like the denominators are always 6, 4, 3 working out from the x-axis. So you can rely on that. I only remember it because I equated to, I like baseball, so 6, 4, 3 double play. I don't know, it doesn't mean anything mathematically, but for some reason that sticks in my mind. The first quadrant is always pi. 1 pi, perhaps, for the first quadrant. In the second quadrant, the numerator is always 1 less than the denominator. So whatever the denominator is, the numerator is always 1 less than that. Third quadrant, the numerator is always 1 more than whatever the denominator is. So you can rely on that. The fourth quadrant is a little iffy. I mean, there's a mnemonic for it, but I don't know that you're going to like it. You take whatever your denominator is, double it, and subtract 1. Okay, so your numerator is 2 times your denominator minus 1, whereas in the third quadrant it's a little nicer where the numerator is the denominator plus 1. In the second quadrant, the numerator is the denominator minus 1. So things like that might be helpful. I mean, if you go on YouTube and look for memorization tricks for the unit circle, you'll see definitely hundreds of them. I'm not willing to go as far as to say thousands, but everybody seems to have what they think is like the best trick to remember the unit circle. So find one that you like and go with it. But developing mastery of this I'll call it simple concept, but really I mean a basic concept in that it is the basis of trigonometry. When you take linear algebra, you'll start to know what basis means.
So basically, I can find any degrees with that, right? I can know what degrees for half of it, and just find out the coordinates of it.
Yeah, but I mean, there's a little bit more to it than that because you have to use sum and difference rules. But it all starts with these measures. So I can do that real quick, only because I want to see if I was right about that one question. This won't be on the quiz, obviously, because I said it was only on the unit circle. But for example, if I wanted something like the sine of 15 degrees, it's not a unit circle number, but it can be thought of as the difference between two unit circle numbers. For example, 45 minus 30. So the difference identity for sine. Sine of A minus B is equal to sine of A times the cosine of B minus cosine of A sine of B. That's it's one of those rules that's like, it's so crazy looking that your pre-calc teacher probably said, put it on your note card. Or maybe they even gave it to you as like a reference sheet on a test or something like that. They probably didn't really ask you to memorize it. But then it doesn't become intuitive if you don't have at least a sense that it exists. So what I would say, if I want sine of 15 degrees, I would designate the A value as 45, so sine of 45, cosine of 30, that's my B value, minus cosine of 45, sine of 30. And just based on knowledge of the unit circle, you can get these values. Radical 2 over 2 times, all right, so now I know I was wrong. It is radical 6. All right, well, anyway, I think it's radical 6 minus radical 4 over 4, actually. But anyway, so radical 3 over 2 minus radical 2 over 2 times the 1/2, all from the unit circle. So sine of 45, that's the y value at 45. Cosine of 30, that's the x value at 30. So just based on, well, my mental snapshot of the unit circle, I get those measures. So radical 6 minus radical 2 all over 4. But obviously the unit circle would get pretty funky if I start including things like that. I'm pretty sure the one for cosine 15 degrees is radical 6 plus, oh, actually it might be radical 2 minus, but anyway, it would be something else, comma, this as the coordinates at that location. Definitely not user-friendly, but still very meaningful.
What's something like this?
Yeah, you